What we have here today is a demonstration of switch bounce. Even though this is a pretty good switch, good quality, it still demonstrates switch bounce, which is not surprising. This style of switch has two contacts that are open or closed, and when they close they can bounce together because they're hard metal, and you get that bounce. We have a 4700 ohm resistor here. We're putting 5 volts into this thing. And I will show it to you shortly on the oscilloscope what switch bounce looks like. But here's the basics of our circuit. It's pretty straightforward. We got the probe tip on right here, and then we got the ground side of the probe over here. Switch at the moment is opened. You'll see when you look on the oscilloscope on the trace, it will start at 5 volts. And if this was an ideal switch, it would go immediately to ground and it would stay there. Switches aren't quite so ideal, like especially this kind here. So here's what it looks like on the scope, and you can see there we got 15 hits on this. That's where it crossed the trigger. Our trigger level here is about 2.5 volts. So this up here is 5 volts. This down here is ground. And in between, before this switch finally settled down, it went back and forth and back and forth. You can see here where it started out, and then it bounced a few times, and then it kind of stayed high open basically for a little while, and then it tried again and eventually ended up over here. These crossings, which happen 15 times, these are triggered on the downward going slope here. So that's where the 15 hits came from. I can zoom that out a little bit, or zoom in a little bit as it were, and we can see where some of these came from. And you'll notice in here there's actually more junk that showed up, like right here and here, but they never came up high enough to go across the trigger line and then back down again. So there's excess stuff in there as well, and there's quite a lot. If I put the trigger down at say 1 volt or something, you would have seen a lot more counts. So now we have a slide switch here. We'll give it a shot and see what happens. Oh, we got 2. When I pulled this out of the bin the other day, and I first hooked it up, it had been probably in the bin for 20 years or so, and I was getting 300, 400 bounces off of this thing. Now, of course, it doesn't really have a bounce per se. It has dirt and corrosion, oxidization. Now, I've probably operated it 40 or 50 times now, and each time I do it, it gets a few less and a few less. So I've put the bouncy switch back in of the ones that we've tried, and a few more components are in the circuit here as well to try and get rid of some of those bounces, if not all of them. And what we have here is a couple of 22K resistors, a fairly fast, low voltage, small signal diode, and a 1 nanofarad capacitor. So what happens here is the capacitor charges through the 22K ohm through the diode and gets basically up to 5 volts here eventually, which doesn't take all that long. And then when we throw the switch closed here, this gets drained, the capacitor gets drained out through the 22K resistor. Yes, this is in the circuit, but we're concerned about this point right here. So we're going to have a look, and we got the oscilloscope hooked up across this capacitor effectively. And we're going to see what, instead of those big spiky things, what we had before, what do we have now when we activate our switch. And there we go. That's the capacitor draining. That's an RC time constant going on there. And we can see from this that we have 2 milliseconds per division. So we've got, let's call it 2, 4, 6, 8, 10. Basically, it gets down to pretty much 0 in 10 milliseconds. So 1/100th of a second or so. For most things, if we're going to be using switches, we're not going to be having them go back and forth 100 times a second. It's unlikely. So that's cleaned that up pretty nicely and taken care of all those little spikes. And I'll get this hooked up over to our Schmitt trigger here, which was the other video from a few days back, to clean this up. The problem with a waveform like this guy that we see up here is that if we're putting this into some digital circuitry, quite often your high level is above a certain value and your low level is below a certain value. In between there, that's undefined. So you have no idea what the circuit itself is going to do. This voltage in here plus a little bit of noise can get your input to whatever this is going to. It can get it to be anywhere. So we're going to stick it through the Schmitt trigger here to clean that edge up, which is that slope up, and give it a nice sharp edge. So I've taken the cleaned output from our filtering circuit, this guy here, and we have that still hooked up to channel 1, the yellow trace, and I'll flick the switch shortly and show you what happens. So this cleaned output is going over to our Schmitt trigger circuit from the other day when I did the video about the 555 used as a Schmitt trigger. Very simple, as you can see, of course. We went over that. And there's that cleaned output coming in to pins 2 and 6 here. And on the scope I have channel 2, blue, set up as this spot here, because this is our pin 3 is our output. And you'll notice that it's an inverting setup here. When this is high, that'll be low, and vice versa. So let's give it a flick of the switch, and you'll see right now, of course, it's on. And I'll flick the switch, and the LED goes out. You can see the cleaned part there, the falling trace here. That's our cleaned output from all those bounces. They're gone. So when it hits the Schmitt trigger voltage, now you notice it's going down, and then that output goes high, which turns off the LED, because of course the LED is hooked from the 5 volt, which of course is the high side. The LED is wanting to see this side go low. Now it's high, so the LED went out. That's the basics of cleaning up a nice signal. And you can see our rise time here. Now I'll take and throw the switch in the other direction. I'll set it for a single sweep again, and we'll go in the other direction and turn the switch. We see our light comes back on. We see our rising voltage here from our cleaned output, and then when it gets to a certain point right here, our Schmitt trigger activates, and it goes low and turns our LED on.